Yeah, hello everyone. Thanks for coming. I wasn't exactly sure what I ought to talk about, and I have to confess I made this talk in like a little bit of haste. I didn't even have time to make the background of the slides red. So here are just some things that were like on my mind, but maybe if you have questions or we can talk about things, it'll be fine. Okay, so first I'll start with some classical stuff. Yeah, the slides just look like this. Anyway, let's say like chi1 through chi-n are like symbols that you're supposed to assign to the numbers plus or minus 1. So formally chi-I squared equals 1. And then like you have this, linear polynomial where this sum of ci chi-I, where the c's are real constants given to you. And you're trying to optimize it. So you want to find opt of L, which is like the maximum value of this linear polynomial under any assignment pi that maps the chi's to plus or minus 1. So I do like to distinguish between like the variables, the indeterminates, which are like symbols, and like the assignment to the variables, which is pi here. Well, this problem is easy when it's a linear polynomial. The optimum value is the sum of the absolute values of the coefficients, which I'll denote by like the 1 norm of c, because you should just set chi-I to be the sign of ci. And I know like physicists like to minimize and computer scientists like to maximize. I guess being a computer scientist, I chose to maximize, but it's all the same. Okay, so we may want to make it harder by having pairwise interactions. So maybe now we'll look at like a degree 2 polynomial that looks like this. It's like the sum of Cij times chi times chi. And it's nicest for symmetry if you assume that Cij equals Cji. And also I have the assumption here that I does not equal j, because there's no point in putting in like a term with I equals j, because we have this rule that chi squared is always 1. So this part never varies, a part that's constant, so we don't need to worry about it when optimizing. Okay, so what can we say? Let's just understand what we can say about the optimum of this quantity. Well, we'll start with some very trivial bounds. So we have an upper bound. Again, the optimum is at most like the L1 norm of the coefficients, which I'll continue to denote like this, even though it's like Cij, because okay, this quantity is always at most plus or minus 1. So that's a simple upper bound. I have a lower bound that the optimum is at least 0. It's actually a little bit non-trivial. Here's the proof if you haven't seen it before. I'll give it very fast. So you can imagine choosing a uniformly random assignment where you just assign each of the chi-i's plus or minus 1 uniformly at random. And then you can look at the expected value of this assignment. And then by linearity of expectation, the expectation of each term under a uniformly random assignment will actually be 0. So the expectation of the whole thing will be 0. And that means, of course, there has to be at least one assignment that makes this degree 2 polynomial at least 0. So that's nice, it's at least 0. And you can, if you're not satisfied with this kind of existential argument, you can efficiently de-randomize this. But actually, it's better to just say that like it's fine for your solution concept to be a probability distribution on assignments, with the figure out of merit being like the expected value which it achieves. That's fine. Actually, if you tweak this argument a little bit, I'll call this an exercise. You can show something a tiny bit bigger. You can show the optimum is always at least 1 over n, the number of variables, times this L1 norm of the coefficients. So okay, like given h, it's somewhere between like the L1 norm and 1 over n times the L1 norm. And that's a pretty wide gap if n is big, but we can try to narrow it down. Okay, so this is lower bound, and this is an upper bound. Okay, well, I'm talking about bounds because, as you probably know, you don't hope to compute this optimum exactly in polynomial time because it's NP-hard. And it's a well-known reduction from the max cut problem on a graph, which is an NP-hard problem. And just to state it briefly, so I'll call it an exercise. If you take the graph and let A be the adjacency matrix of the graph, and then you basically let the Cij's be like the negative of the adjacency matrix. So like all the Cij's are minus 1 if there's an edge between I and j. Then it's not hard to check that the maximum cut in the graph, the maximum number of edges that you can cut by the best partition into 2 parts, is basically the optimum of the resulting degree 2 polynomial. It's like 1/4 times the optimum plus 1/4 times the sum of the absolute values of the coefficients. Anyway, like this is a number that you certainly know. You're staring at the graph, so you know this quantity. So, optimizing this h that you get from the graph is the same as optimizing this. So if you can't hope to compute this exactly, you can't hope to compute this exactly. There's maybe some seats over there, I don't know. Okay. So let's go back to bounds now that we have this sad feature that we cannot compute it exactly. So here's a different upper bound that's also easy to compute in polynomial time. It's the maximum eigenvalue of the matrix you get from putting these coefficients into a matrix times n. And we can compute the maximum eigenvalue efficiently, so that's a nice upper bound. And let's see why this is true. If you have any assignment pi to these n chi's, and you stack pi in just a vector of plus or minus 1s like this, and then you do this quadratic form like pi transpose c pi, it's easy to check that that equals the value of the assignment pi on h. But then from linear algebra, this quantity is always at most the maximum eigenvalue of c times the product of the lengths of these two vectors, so the 2 norm squared of pi. But pi is a vector that has all plus or minus 1, so its 2 norm squared is n. So that establishes that bound. Okay, so now we have this two different upper bounds. And actually, either of these upper bounds might be better than the other one. So I'll give some example. Here's a trivial example. Imagine this is your whole polynomial, just chi1, chi2. But imagine there are n variables. We're just choosing not to use them. All the associated coefficients are 0. Then the sum of the absolute values of the coefficients is 1. That's upper bound 1. And that's actually also the optimum, 1. But lambda max of this matrix is, I think, half if I calculated it right. And so upper bound 2 is n over 2, which is much worse. On the other hand, here's a different example that's I don't know, physics, motivated from physics. It's a case where it's the instance where you choose all theCij's it to be independent Gaussians. It's called the Sherrington-Kirkpatrick model. So if you choose them at random and then fix them and study the optimization, the maximum value of this, well, the upper bound 1, the sum of the absolute values of the coefficients, there's basically n squared terms, and the absolute value of a Gaussian in expectation is some explicit number. So this first bound is proportional to n squared with high probability. But then it's also a famous theorem. If you have a matrix full of Gaussians, the largest eigenvalue is 2 root n with high probability. So then we multiply that by n, and you get something that's proportional to n to 1.5. And that's much smaller. So this is an example where upper bound 2 is smaller than upper bound 1. And incidentally, they know that the optimum is, it's smaller than this by a constant factor, but it's proportional to this. Okay, so that's a bit funny to have two different upper bounds. That one is sometimes better than the other. So you might ask, can we get a common generalization of upper bounds 1 and 2? So some easy to compute quantity, which is an upper bound on the optimum, but always at least as good as upper bound 1 and upper bound 2. Any suggestion? So you're sitting all here in silence. I know you know. I know some of you know. Yes, thank you, yes. Yeah, there's this SDP bound. So let's talk about that. So the optimum value of h is the maximum, of this assignment to h that you can get by plugging in plus or minus 1s. But if you also allow your solution concept to be a probability distribution over assignments, then you can say it's the maximum overall probability distribution on assignments of how much that assignment gets in expectation. And even if there's one optimal assignment, you can have the probability distribution that puts 100% of its probability on that assignment. So this is an equally valid way to express the optimum. Okay, so now if you imagine having a probability distribution P on assignments pi, you can make a matrix that encodes, I don't know, how correlated the assignments to each pair of variables chi I and chi j is. So let's make this matrix M, it's n by n, whose ij entry is the expected value under the randomly chosen assignment pi from P of the assignment to chi I, chi j. And we can make some observations about this quantity. Let's first observe this one. Like the diagonal entries MII are always 1, because chi I squared is like 1 by definition. And it's easy to see, kind of similar to the calculation with the matrices on the last page, that like this quantity we're interested in, the expected value of the assignment, is some function of this matrix of moments and the input c's. It's actually just trace of m times c. So everything you need to know about the objective value is encoded in this m. And finally, there's this further observation that for this matrix m, just let a1 through an be any real numbers and look at this quantity. Well, for reasons similar to what we saw in the previous slide, and by the definition of m, this expression equals the expected value when pi is drawn from this distribution of pi, what pi gives to the square of this linear form, sum of ai chi I. And okay, the square of a number is not negative, so this whole expression has to be non-negative. But then if you just forget that calculation and see that it tells you that for any vector A, like A transpose M A is non-negative, that's the definition of M being a positive semi-definite matrix. So this matrix M has like several properties here. And so if you just forget the fact that like maybe M arises from an assignment and just remember like these facts about it and optimize over M's that satisfy these facts, then you're relaxing the problem. So you might get like a bigger value, but that's what we do when we study this SDP, which is the maximum over all PSD matrices with 1s on the diagonal of the trace of M times the input numbers C. And the value of this optimization problem we'll call SOS2 of H for reasons that I guess I won't explain, but will come up later, the day I'm sure. And this is an example of a semi-definite program, and it's known that like you can solve them in polynomial time, so this optimal value is easy to compute. So it's an easy to compute upper bound on the optimum. And moreover, I guess I'll call this an exercise for you. You can show that this optimum is always less than or equal to upper bound 1. And it's also always at most upper bound 2. So it's like it's at least as good as all the previous upper bounds. Any questions right now? Okay. Great. So when you make this SOS relaxation, this SDP relaxation, like the inherent nature of it is like it's an easy to compute number, which is an upper bound on your answer. It's like a certificate that the optimum value for this H is at most the number that it spits out. And that's good to have like a certified upper bound on the optimum of H. You might also want like a certified lower bound. So a certified lower bound is like, something you can be sure tells you is a lower bound on optimum. And more or less the way you would ever get such a thing is to like somehow exhibit like a pretty good assignment pi. For every pi that you exhibit, you compute what value it gives to this expression H, and that gives you a lower bound certificate. Now, of course, once you do that, you would like to compare, you would like to understand how good is this? Like, is it close to the optimum or what? So ideally, you would like to compare like the value pi achieves to the opt. But there's this like philosophical issue that like opt is like an NP hard to compute quantity. So like probably like any math proof you write can somehow like not really access what opt is. Like you can somehow only access, this is a heuristic guide, but like quantities which are computable in polynomial time. So somehow we therefore usually end up comparing, how much a value a pi gets, not to the opt, because we don't know what it is, but to like this even larger number, like our best, known upper bound on opt. Which in this case, well, a good thing to compare to in this case is this SOS or SDP value. And because of that, we often see this concept of like a rounding algorithm, which says, take the optimum of this optimization problem. You can figure it out, and you can figure out m that achieves some value. And rounding refers to the concept of trying to take this m, which achieves the optimum for this SDP, and converting it into like a legitimate assignment pi that achieves an amount that is, gets on H an amount that's at least some, I don't know, fraction, let's say, of what m is getting in this program. So, and that, of course, is at least the same fraction of the optimum. So that's like a paradigm that's often going on. Okay, so in this context, let me highlight a key result like this due to Nemirovsky, Roos, and Terlaki from 1999. And they did exactly this. They came up with an efficient rounding algorithm that takes this optimal SDP solution m and converts it into an actual plus or minus 1 assignment pi, which is real good. I mean, pretty good. It always gives you an assignment that's at least a 1 over log n fraction of this upper bound. So at least a 1 over log n fraction of opt. And that's pretty good. Like, log n, 1 over log n is not so bad. I mean, it's much better than like the algorithm implicit in this thing, which gives you like a 1 over n fraction of your upper bound. So like 1 over log n is not bad. This is like an extension of the Gomans-Williamson rounding, if you've heard of that. And so this is actually reasonably satisfactory. So even though it's NP hard, this is decent. Actually, there was an improvement to this, suggested by Feiga and Langberg in 2001, and then analyzed by Charkar and Wirth in 2004. A little bit complicated to state, so let me go through it. It's a rounding algorithm that takes this SDP solution m and converts it into a genuine assignment pi. And it's parameterized by a t that you, the algorithm's user, get to choose. And it produces an assignment whose quality is at least this. It's a lot of symbols. It's basically whatever t you choose, you get an assignment whose value is a 1 over t fraction of the optimal SOS value. Except there's an error. That looks good. You're like, I will choose t to be 1. But there's an error that could be as large as this. So the error gets smaller the bigger t is. And it's like multiplied against this naive upper bound, the absolute value of the sum of the absolute value of the coefficients. So let's say you solve your semi-definite program and you get this number, SOS2 of H, which is an upper bound on the true optimum. And you're like, hey, it's actually reasonably large compared to this super naive upper bound, the sum of the coefficients. So let's say it's at least some epsilon times the sum of the coefficients. Great. Then you say to yourself, okay, like I know this term is at least epsilon times 1 norm of c. So if I were to do this Charkar-Wirth rounding, I would get a solution with this amount. And then this amount I can just like optimize myself. You should optimize it by choosing the best t, and the best t is, any quick-witted people out there? The best t is proportional to log 1 over epsilon, yeah. So if you then select t to be log 1 over epsilon, then you'll get this. This will be like epsilon over log epsilon, and this will become like negligible if you make this constant here large enough, which maybe I should have written. And so the quality, the value of the h you get out of this algorithm is at least epsilon over log 1 over epsilon times this bound. So if your upper bound was epsilon, you get an assignment that's like epsilon over log 1 over epsilon. And that's pretty good. And as I'll say in the next slide, that's like actually even better than, or at least as good as this. But that's good. And if epsilon is 0.1, then like this is just some other constant, and you get like a slightly smaller constant than 0.1. So it's kind of like an approximation factor of 1 over log 1 over epsilon. It's kind of funny because the approximation factor, if you will, depends on what the actual value epsilon is. But as I mentioned, it's always better than this one because this epsilon is never worse than 1 over n because of this thing. Op is always at least 1 over n times this L1 norm, so SOS is always at least 1 over n times this L1 norm. So this epsilon is never worse than 1 over n, which means this factor is never worse than log n. So it's at least as good as this one. but that means we can just forget about this one. Yeah, and this is quite nice. Actually, okay, now that we have this, we can ask a related question. Is like, what if you solve the SDP and you see that the upper bound on this solution is actually not just like a decent fraction of this naive upper bound, but it's actually really close to the naive upper bound, which is, so it's like 1 minus delta times the naive upper bound. Then the Gomans-Williamson algorithm, which you possibly heard about, a rounding algorithm, can convert this into a genuine assignment that's also like really close to the naive upper bound, but it's like 1 minus square root delta times the naive upper bound. That's still pretty good. Goes from like 99% to 90% or something like that. And while we're here, a related fact from Umesh and others says that if you don't like, yeah?
Why is it good to be close to the naive upper bound? I mean, the naive upper bound is the one you get with any assignment, right? So it seems that you haven't really gained anything.
Oh, no, well, the naive upper bound, it may be that your instance like doesn't have an assignment that gets anywhere close to this. Like if you remember the Sherrington-Kirkpatrick example, like there, this naive upper bound was like n squared, but the actual optimum is like n to the 1.5. So there would just be a setting where like, I mean, this is not the case. But if you happen to be in a setting where like you can actually kind of, it's very close to the situation where you can get like sort of all the terms perfectly right. Like you get arrange for all the signs to be the same as the C's. If you happen to like, discover that you're in that setting, then you can actually find an assignment, by virtue of this, you can actually find an assignment that's like sort of almost equal to the upper bound, the naive upper bound. But it's a particular case. Like, I mean, this is basically, it's not always applicable. Yeah, I was going to say, if you don't like the square root here, like an alternative, which is also pretty good, is, well, you need the triangle inequality if you know what that means. But if there's a generalization of this SOS2 thing to SOS4, and if it's sufficiently large or sufficiently near the naive upper bound, then you can find an assignment that's also, in a different way, close to the naive upper bound. It's 1 minus root log n times delta. Yeah, so I'll just remember the first one. And by the way, you might hope to, I don't know, make this better than epsilon over log 1 over epsilon, or you might hope to make this better than root delta, but we know that actually doing this is probably hard. It's unique games hard up to the constants. And this one is sort of, at least I feel like morally unique games complete, like trying to get like 1 minus delta to the 0.51 here is kind of the same as the unique games conjecture. Any questions right now? I think, yeah, I just want to say that these results are pretty good. Like degree 2 is like a case where you can actually do some interesting stuff one sec, and things are much, much harder as soon as you go to like degree 3. You can encode 3-sat and so forth. So degree 2 is a nice case to study. Yeah, Anand?
Is there a similar story when you're really close to upper bound 2?
I don't know. I don't know of one. Does anybody know of one? I guess it's kind of like, maybe, I don't know, is Siddhant here? It's kind of like, this is like, you feel that perhaps like there's like a Boolean vector that's like almost in the eigenspaces that are achieving the highest eigenvector. So maybe you feel like, oh, I can just combine these eigenvectors to get like a Boolean vector.
Like, isn't the proof of Cheever's inequality something?
I think it kind of resembles, well, I don't know. Maybe, do you have anything to say? I'm sorry, I'm really putting you on the spot. Okay.
Yeah, I don't know off the top of my head.
Okay, let's put a pin on it, and that's going to be one of the things we discuss afterwards. Good question. That's all I want to say about classical stuff. So now I'll start talking about quantum stuff. Is there a clock in here? Yeah, okay. I might not get through all the quantum stuff, but that's okay. We're just here to chat. So I guess the vibe in quantum stuff is that things are now matrices instead of numbers. So let's imagine a similar problem where chi1 through chi n are now to be assigned square matrices. I'll explain what I mean here a bit more. But we're also, because they're matrices and they're going to have complex numbers, it's not a big deal, but we'll also introduce the symbol chi I star. And like whatever matrix pi assigns to chi I, it ought to assign the dagger of that to chi I star. And we'll also introduce the symbol 1, which is supposed to always be assigned the identity matrix of whatever dimension your assignment pi is using. And we're going to insist that like chi I star formally equals chi I. So look, that basically means you're supposed to be assigning Hermitian matrices to the symbols. And like before, when the chi I squared equals 1, we're going to continue to require that. You don't have to, but let's continue to require that, which means you're assigning reflection matrices to the symbols now. And yeah, I don't know how much I'm going to say, how much sense it will make. So please ask questions if I start to be confusing. So before we get to optimizing polynomial expressions in these symbols, we're going to actually insist on more things. Let's talk about insisting on certain commutation or anti-commutation relations. And I'll bring this a bit down to earth in a moment. But here's an example. And this is related to some paper I wrote. And I'm not supposed to talk about my own work, but I think it's a helpful setting to think about. So imagine I just has another feature of the optimization problem. I insist that you assign to these symbols matrices that pairwise anti-commute. And there do exist matrices, a bunch of matrices that all pairwise anti-commute. So this is not a vacuous or an impossible task. Okay, so let's think about this a bit. So let's say we'll start at degree 1. So you're given this formal polynomial expression. The c's are real numbers. And we're even trying to optimize because you're supposed to assign, pi is supposed to assign these symbols to matrices that are reflection matrices that anti-commute. What are you trying to do? You're trying to maximize the maximum eigenvalue of the resulting matrix assignment. Okay, you're trying to maximize the maximum eigenvalue, or the minimum eigenvalue if you're a physicist, over all the assignments of pi's to matrices in your choice of dimension, that's up to you, that satisfy the requirements. This problem is actually, the linear case is actually easy, because a funny thing happens. If you just take this expression formally and square it, or Hermitian square it, L star times L, doesn't really matter in this case. If you just expand it out formally, okay, you get ci squared times chi I squared. Chi I squared is the identity, so you get sum of ci squared times the identity. And then in the cross terms, you'll get c1, c2 times chi1, chi2, but you'll also get c1, c2 times chi2, chi1. But they anti-commute, so those terms cancel. So it's a funny situation. If you just formally expand the square of this, you get a number, or the number times the symbol 1, which is the squared 2 norm of the coefficients. And therefore, actually, any assignment that satisfies all the requirements just must map the square of this resulting matrix to this number times the identity matrix. So its largest eigenvalue will be this quantity. Okay, so here, you don't even have a choice. It's the optimizer. No matter what you do, the value you get will be this 2 norm of the coefficients. Okay, hey, great. That was an easy case. Why you might study this situation, I'll say a little bit about shortly. Okay, so naturally you're okay, let's make it harder and go back to degree 2 again. So here's what I've written for the degree 2 case. Now there's something funny here. You see, I stuck in this factor of I, literally meaning the square root of -1 here. Why do I do that? Well, chi j chi k is not self-adjoint. If you star this, you want it that if you star this, you get the same expression back. Basically because you want it to be the case that like any matrix assignment to this thing gives you a self-adjoint matrix, because then it has real eigenvalues and it's sensible to ask about what is the largest of these eigenvalues.
C's are real.
C's are real, yeah, I didn't write that, but C's are real. I mean, you don't, yeah, let's just say C's are real, keep it simple. And also, this is a very minor comment, but now if you're stacking these C's into a matrix, because of this anti-commuting, the natural way to do it will make an anti-symmetric matrix. But it's not a big deal. Yeah, so this is self-adjoint, because if you like star this, you get a minus sign here because of the I, but then when you like undo this swap due to anti-commutivity, it gets back to this. But don't stress out about this too much. It's like this is a natural degree 2 polynomial in these symbols that you would try to optimize. And maybe here's a reason you might try to optimize this. I'm sure like 100 people in this room know better than me what's going on, but I guess like such Hamiltonians can be used to model like the situation where you have n/2 fermions with like one-wise interactions. And you might be like, I was like, wait a minute, like isn't this pairwise interactions? But I guess like fermions have like are associated, like one fermion is associated with one creation and one annihilation operator, and yada yada yada. Like this somehow models one-wise interactions. Okay, and therefore you might be interested in physics reasons for optimizing this. Although it's not really the way they think about it, but it's equivalent. And it's because, so I phrased this to like match the classical stuff. I phrased this as about finding like the best matrix assignment to like make the resulting matrix when you substitute into this H have as large eigenvalue as possible. But actually that's kind of misleading, because once you have like these anti-commuting constraints, there's basically like a unique assignment, pi. It gives you an exponentially large matrix. You need exponentially large dimension in order to find these matrices that pairwise anti-commute. But basically, there's only one. In some sense, like up to unitarily conjugating all the matrices simultaneously, which doesn't change the maximum eigenvalue, and also up to like stacking them in a direct sum fashion, which also doesn't change the maximum eigenvalue. So in some sense, like in this problem actually, there's no like search aspect to it in a certain sense. Like you have to understand an exponentially large matrix represented in this implicit way. Yeah.
Because it's quadratic in fermions, isn't it exactly solvable?
Yep, that'll be on a slide coming up. Yep. Okay, and actually this is I have only one like message I'm trying to get across actually in this talk, which is the vibe. And the vibe is, don't even worry about like what are these matrices. I could tell you these matrices, you can write down a formula that like all like n matrices that pairwise anti-commute. Don't even worry about it. The vibe is, never worry about the matrices, only think about the relations, like the formal algebraic relations of the symbols. That's the vibe. So how can you do that? Let me try to understand how you can do that. So, okay, I told you you're trying to, let's think about it like in a previous way. You're trying to find the largest of pi, or maybe it's this unique matrix assignment pi. You're trying to understand the largest eigenvalue of it. Well, the largest eigenvalue of a matrix, probably or possibly another way to express it is like it's the maximum possible value of trace of rho times that matrix over all density matrices rho. Matrices that are PSD with trace 1. It's just a little linear algebra fact. Now, a cool thing about complex square matrices is that an actual matrix is PSD if and only if it's a square, like the Hermitian square of another matrix. If and only if it's like the Hermitian square of some other matrix L. So like this is like a perfect SOS scenario. You're like positive if and only if you're a square. So that's nice. So now, okay, here's like the trickier part. This is var rho, right? Let var rho be a formal polynomial like this one in the symbols chi1 through chi_n. And I'm going to call such a formal polynomial in these symbols a state. if two things happen. First of all, it's the Hermitian square of some formal polynomial. And its trace is 1. But what is a trace of a polynomial, formal polynomial? It just means the constant term, the coefficient of like the symbol 1. Okay, so in some ways this is like you can, I'm kind of allotting some details here, but this is like you can think about states or density matrices back in the world of like polynomials. Oh, yeah. And so it turns out, I mean, by thinking about this for a moment, you see that you can equivalently define the optimum of this formal polynomial only in the language of like formal polynomials, and forget matrices. It's the maximum of the trace of rho times h. This is what you get when you multiply these two formal polynomials together, and trace is just like, please tell me the constant term. Where the max is overall states rho, and a state, remember, a rho is a state if it's like the square of something, and its constant coefficient is 1. I'll give an example sort of here. But like what's nice about it, and it connects to the message, is now everything is happening in the algebra of formal polynomials. There's no matrices anymore. And like, I encourage you to sometimes think about your problem in this way, if you can. So, okay, yeah. So this is, I've been talking for a while about this running example where like, oh, I put as like a side condition, all the symbols have to anti-commute. But you're probably like, I don't normally study that situation. Like, I'm into like, I don't know, like, well, here's another different example. Let's say I say like, oh, no, all the symbols commute. That's my new rule. All the symbols commute. But it's the same problem. So in principle, you're searching for an assignment of matrices to these symbols where all the matrices pairwise commute, and you're trying to make the assignment value for h have the largest eigenvalue possible. And in that situation, you'll probably start thinking these thoughts, like all these matrices commute, so they're like simultaneously diagonalizable, so I may as well just do that. That doesn't change the eigenvalues. And as you'll see, it actually just turns into like the classical problem from the first half of the talk. But you can also see this at the level of polynomials. We can still say like, all right, it's a persistent bug. This is our definition of the opt. And again, in this world where they all commute, there's somehow like a unique maximal assignment pi of these symbols to matrices that encompasses all the sort of distinct possibilities. It's the one, again, don't be too excited about the matrices, but it's the one that looks like a Pauli string with like a z in the jth position. These are matrices that all pairwise commute, n of them. And yeah, because of this, it follows that like the classical problem we studied in the first half of the talk is like equivalent to this like optimization problem in the land of polynomials where you just don't even think about assignments too much or like matrices, just you think that the symbols commute and square to 1, the identity. So yeah. And here's a fact, like if you want to connect the sort of assignments of plus or minus 1 values to like states and so forth, for any like string of plus or minus 1s, that might be the assignment values. This var rho, which is a formal polynomial, is a state. If you multiply all this out, the constant term will be 1. And it doesn't look like it's a perfect square, but actually it is a perfect square because like, if you think about this for a moment, if you like square this factor and like use that chi I squared is 1 and that this chi's commutes, well, you don't need that yet. You'll get that like the square of this is basically itself up to a factor of 2. So this is a square, and this is a square, and this is a square, and they all commute. So like this whole thing is a square. This is not like super important to follow, but yeah. And just to connect it to this funny way of thinking about it, the trace of this state times the Hamiltonian, if you like multiply this all out and keep the constant term, it's just the value of the classical assignment of like these chi's getting these plus or minus 1 values. Yeah. And also, by the way, like under this unique maximal assignment of these like Pauli strings, this state is a matrix. And what matrix is it? It's just a pure product state of ket zeros and ket ones. Okay, so back to the the setting where, let me go back now to the setting where all the variables pairwise anti-commute. And one thing I want to say is like this is a very nice, the reason I like actually kind of harp on this example is it kind of simulates all the other examples that you might study. So what do I mean by this? So let's say if you're in the world where all your symbols anti-commute, you can use this to simulate the world where all the symbols commute, and therefore you can use it to simulate the classical problems we discussed in the first half of the talk. So why? Well, take your n symbols that are supposed to pairwise anti-commute, and if you just pair them up into pairs, you have to do this stupid thing of multiplying by I to make it self-adjoint. These, n over 2 many little degree 2 expressions are like symbols that are self-adjoint, and they square to 1, and they pairwise commute. So you can think of them as like new symbols. They have the right algebraic properties. They pairwise commute. So like you can use these little symbols to like set up like a classical problem, right? So if you're interested in the classical problem of like optimizing sum of ci times one variable, you just do like sum of ci times this plus this plus this. Now when you do that, actually, you would take a degree 1 classical problem, it would become like a degree 2 problem in this like simulation world. So you might think like, oh, I made the problem more complicated, but hang on, maybe you didn't make it so much more complicated. In general, you can simulate the degree k commuting classical problem in the degree 2k anti-commuting setting. And it also simulates, if you're really into like k-local Hamiltonians, which I think many people are, same story. It's you can also simulate it, the k-local with degree 2k here as well. And why is that? Well, here's the trick. Let's say you have a k-local Hamiltonian problem with n qubits. Well, you're like, oh, I'll take 3n anti-commuting symbols, and like here, instead of calling them chi1 through chi3n, I'm going to call them alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2. But like, think about it, you're like, oh, all 3n of these variables pairwise anti-commute. But now, in a similar way, you like, oh, let's make some little degree 2 monomials out of these guys. Let's look at alpha j times beta j and put the stupid I in. And like also alpha j times gamma j, and also beta j times gamma j. These little 3 degree 2 polynomials exactly satisfy the Pauli relations. Like, what are the Pauli relations? This one times this one is negative of this one, for example. It's a 1 second exercise using the fact that everything anti-commutes. And moreover, like, alpha 1, beta 1 commutes with like alpha 10, beta 10. Like the different groups pairwise commute. And so again, if you're in this like vibe where like the only thing that really matters is the algebraic relations between these symbols, and you forget about matrices and everything, then yeah, you see that okay, you can simulate like k-local Pauli Hamiltonians is a special case of like optimization in this fully anti-commuting world if you're willing to increase the degree by a factor of 2. And so for example, like, I don't know if this is like a good idea, but like if you're into like quantum max cuts, it's the same as like optimizing a special kind of degree 4 Hamiltonian in this setting, where like every term kind of looks like it's like a positive linear combination of terms that have this special form. Okay. So because of that, like, okay, this is like a pretty general setting. So let's think about it for a moment. We'll get back to the question from earlier. Let's think about the degree 2 case of optimization in this world where all your symbols anti-commute, which can simulate, I don't know, 1 local Hamiltonians, for example. So this is at least as hard as like, degree 1 classical or like local 1 Hamiltonians, but those are easy problems. This is at least as hard as those. But as I was pointing out, this problem is also easy. You're like, oh wait, it's degree 2, but it's easy. That's interesting, but it's true. So I won't prove it, but it's like not very hard to show that given a degree 2 expression and these symbols, the optimum is just the maximum eigenvalue of the matrix of C's. Well, times I again. So you can just compute that. And moreover, it's easy to describe and write down a representation of the optimizing state. The actual set of states that like optimize degree 2 polynomials like this has a horrible name. Well, in my opinion, I'm sorry to whoever invented it. They're called Gaussian states, but I don't like this name. And actually, don't really worry about this formula too much. But like, Gaussian states is a class of states, but like, which are like now expressions, like formal expressions that look like this in terms of the chi's. And they have like a, I don't know, a nice simple format that you can write down on a piece of paper. They're actually like, you know, full like degree n expressions, but you can still write them down. And like, given any Hamiltonian, it's easy to evaluate like what is the value you get of that Hamiltonian under this Gaussian state. It's a formula, and like the state of all states that are like this are exactly all the possible optimizers of degree 2 Hamiltonians. Is there a question? So it's a nice class of states. And it's exactly the states you need to solve degree 2. And if you are playing this game of saying like, oh, I'm interested in like, you know, spin systems, local Pauli Hamiltonians, but I'll do this trick of like encoding them with like products of 2 fully anti-commuting symbols. Then under this trick, the class of product states, and you're back in your like basic, you know, qubit spin world, is like a subset of the Gaussian states. So that's also nice. They kind of contain product states in this sense. So similarly, we can go up to degree 4 polynomials in these fully anti-commuting variables, and it's a natural thing to do because from what we said, degree 4 in this anti-commuting case like can simulate, you know, degree 2 classical case or degree 2 like local Hamiltonian case. And we kind of really love this case in computer science, these cases, because like, okay, it is NP hard, but like there's cool stuff to do. You got SDPs, you got approximation algorithms. Sometimes you actually get like good approximation algorithms. So it's like a fun setting. It's not like impossibly hard like the 3-SAT world and so forth. So this is at least as hard as degree 4 in this case is at least as hard as degree 2 in like these more familiar cases, but has the same spirit. Like it turns out that like, oh, sometimes the degree 4 case is also like decently approximable, and like you can get some cool results with SDP rounding and stuff. And particularly, I'm not that familiar with this word ansatz, but like when you use like Gaussian states as ansatz, like there's many different kinds of like states, but like, you know, Gaussian states is a simple class of states that you can try as like your optimizers. Yeah, I'm not sure how much time I have to go through all this, but let me say a few more things. So, yeah, so I hope that motivates you to think a little bit about this case, degree 4 optimization. And you have a similar situation. One naive upper bound is the sum of the absolute values of the coefficients. And another upper bound, this one's not so easy to prove, but like another upper bound is n times the sum, well, the 2 norm of the coefficients. And again, there's this feature that sometimes either of these could be better than the other, but there's a common generalization of both of them, which is like the degree 8 SOS value of this expression, which I won't define, but maybe we'll hear about later today. And it's also computable in polynomial time with the semidefinite program. And maybe similar to the flavor of like completely general like 2 local Hamiltonians, it's actually kind of hard. So like one thing you might do, and this was suggested by Bravi, Gossett, Carnegie, and Tema. This is a great paper if you haven't studied before. They said, well, it's kind of a hard problem, but maybe we should just consider the simple problem of trying to like optimize this not over all states, but over the Gaussian states, because we can understand Gaussian states pretty well. They have an explicit formula. You can explicitly evaluate how well they're doing on like a given polynomial. So you can define this quantity, which will, of course, always be less than or equal to the true optimum. But you know, it's reasonable to decide to be interested in this quantity. And what's also nice is you can write down a semi-definite program that's a relaxation of this. So it's kind of weird. Here's the optimum, then here's the optimum over Gaussian states. But then like here's a relaxation of the optimum over Gaussian states. So these things are a little bit incomparable. But this is a quartic-size SDP relaxation of this quantity, which is natural to think about. And this is sort of a simple thing that they showed. So it's not great, but the first thing you might ask is like, how far could this be from the true optimum when you like optimize only over this class of Gaussian states? Like, is that terrible or is it like kind of good? They show that like it's not terrible. So like the optimum over Gaussian states is at least, well, 1 over n fraction of the optimum, the true optimum. Sorry, the SDP relaxation value is at least 1 over n fraction of the true optimum. And as I'll say on the next slide, there's a rounding algorithm that shows that the Gaussian optimum is pretty close, log n factor, to the SDP optimum. And if you put these together, you get that like the optimum Gaussian value is at least 1 over n log n times the true optimum value. So that's like not amazing, because like these differ by a factor of like n log n, but it's not nothing. And they actually conjectured that perhaps like the optimum Gaussian value is at least a constant fraction of the optimum value, but it turns out to be not true. It turns out that actually optimizing over Gaussian states can be like quite bad compared to optimizing over everything in general. For example, in the case where all these CIJKs are like IID Gaussians, it's called the SYK model, the true optimum is like n to the 2.5, but the best Gaussian state only gets like n squared. So they can differ by at least a square root n factor. So it's not great. At least for some kinds of Hamiltonians, it's not great, but maybe for other kinds of Hamiltonians, maybe simpler ones, like this Gaussian state is a reasonable thing to study. Yeah.
It seems like SOS4 is also an upper-bound to optimum. Where is it? How does it compare? Like, I mean, it's SOS8, right?
Yeah, not well understood. Great question. Like, what can you say about SOS bounds for this problem?
So it's not known if it is better than 1 and 2.
Oh, yeah, it's probably, it might be the case that like sometimes this is not as good as this bound. But maybe you should just always, I don't know, maybe this is the natural, I don't know, 8 is like 2 times 4. So it's like reasonable to give, like even the only reason like it goes to degree 8 here is because like you'd like SOS to be able to talk about the square of this polynomial. That's it. So I'm almost done here, but I do really want to mention this paper. So if you remember way back for like classical degree 2 optimization, there's like this natural SDP, and then this Nemirovsky-Roos-Terlaki paper gave this natural rounding algorithm that was quite good. So this guy, I don't know, Anthony Manchan So in 2009 gave like a non-commutative generalization of this rounding algorithm. Nothing to do with quantum. He was like straight up like an optimization person, but he was motivated to study this. It's like a little known paper. And this paper of Ravi Gossett, Carnegie, and Temes showed that his rounding algorithm is real good for the Gaussian setting, the Gaussian state setting. So like whatever the SDP relaxation for the Gaussian optimization problem is, like this rounding gives you something that's at least 1 over log n is good. And you can similarly generalize this in the style of this Charikar-Worth paper, so that like if this SDP relaxation is close to this upper bound, like it's like an epsilon fraction of this upper bound, you can get an actual Gaussian state that's like epsilon over log 1 over epsilon. So it's like a good approximation factor for this subproblem of like not full-on optimization of this, but like optimization over this nice ansatz of Gaussian states. Okay, I think this is pretty much my last slide. So I don't know, wrote some open questions that occurred to me in this setting. So this result is about if you're like a constant fraction of this upper bound number 1, but what about like if you're a constant fraction of this upper bound, which I think is more relevant for things like a quantum max cut or 2 local Hamiltonians. There, like you're usually comparing yourself, or you feel like you're comparing yourself against like the sum of the absolute value of the coefficients, like the number of edges in the graph, basically. And don't know any results about this. You could also ask the analogous high-end question, like what if the SDP relaxation for Gaussian states is like really close to this upper bound? Can you get Gomans-Williamson type thing? Don't know anything about UG hardness. Another interesting thing is like the Hamiltonians that show that this bound is tight have the property that their optimum is a Gaussian state. So like, it seems, we don't know theorems along this line, but it seems like if you're close to this bound, then maybe actually Gaussian states do well for you. So that's not known. Yeah, like I think we're going to hear about quantum max cut today. And I literally don't know what happens if you just like put quantum max cut into this format as a degree, like a very special kind of degree 4 polynomial, and then maybe apply like So's rounding algorithm to it. What happens? I don't know. Like Gaussian states like include product states, but like it's a bigger class, so maybe something good could happen. And well, let me just advertise this paper by Matt Hastings. I'm probably out of time, but he has some very interesting questions about like how much does SOS know about perturbation theory, which is like the situation where like you have like a simple Hamiltonian, you know it's optimum, but then you add in epsilon times like a complicated Hamiltonian. You know, there's a lot of sophisticated perturbation theory using linear algebra about like how that changes the optimum value, and you can understand maybe SOS can model that perturbation theory. Or, like, I think this is a funny question, like, is there a perturbation theory for SOS? Like, if you have an SOS-style bound, if you know what this stuff means, on like a simple Hamiltonian, and then you slightly perturb the Hamiltonian, can you perturb the SOS certificate for it and get, like, a comparable bound? I don't know. Okay, I'll stop there. Thanks.
What would it mean for, what kinds of things could SOS know about perturbation theory? What could a possible answer be?
Yeah, I'm not an expert on this, but let me try to say a little bit more precisely what is meant. In this paper, like he considers like some basic Hamiltonians, like quadratic Hamiltonians in the anti-commuting setting and the spin setting, and also in this continuous setting with like this funny setting with position and momentum operators. And maybe you'll take like a degree 2 thing which you understand well and add like epsilon times a degree 4 thing. And I guess like in physics, it's really in linear algebra, but like in physicists like study this, like, by like actually thinking about the matrices and thinking about what happens when you like take a matrix whose eigenvectors and eigenvalues you know well, and you perturb the matrix a little bit, how do the eigenvalues change? There's like these 3 different ways of like doing perturbation theory that are named after like pairs or triples of physicists, which I don't know. And they can tell you like what happens up to first order and even second order and any order. And Matt's paper is asking like, well, perturbation theory tells you like it changes by at most epsilon times this expression. Does SOS know that? Like, can you show that like the sum of squares method can also prove like that's an upper bound up to first order? And he really just does it by like kind of the first like grungy like thing where you just like, I know what the answer is, I'm going to try to express it as the sum of squares. And sometimes he's able to do it, and sometimes he's like, I don't know how to do it. But I don't, maybe this is like a wacky idea, but like, if SOS understands the simple Hamiltonian, you express like the Hamiltonian minus the maximum energy or whatever as a sum of squares, and then you perturb the Hamiltonian, is there a way to like perturb the sum of squares representation that would like give you a bound for the new Hamiltonian? I don't know, but I think this is like, maybe, I was also interested in this because like, I don't know anything about physics, so I'm like, what kinds of Hamiltonians do people actually care about? They're like actually motivated by physics. And like, this is, I guess, something that people care about a lot. Like you have like a simple Hamiltonian, and then like, yeah, you perturb it by like a epsilon times a more complicated one. Yep.
Earlier you said the degree for anti-commuting cases in some sense a bit more powerful than, I understand that it contains both of them, but in what sense can it be more powerful than, say?
Oh, just in like the strictly, I just meant the strictly formal sense that like literally like you can simulate the degree 2 local Hamiltonian case with degree 4 anti-commuting case. That's it. But plus there are some, you can also express some degree 4 stuff that is not in this setting. So just like strictly at this formal level, that's all I meant by it.
But is there a way of quantifying that it's strictly more powerful, that it can be strictly more powerful?
Well, I guess like you can, like if you're interested in modeling fermionic problems, then you can like with, like only like local interactions, you can do it with like low degree polynomials in the anti-commuting case, but I think you cannot do it except with like, high degree, like proportional to n polynomials in the like the Pauli spin model. Yamato?
Are there any kind of Grothendieck-like results for partite versions of degree 4?
Oh, great question. Maybe. Yeah. So this raises like another excellent point, which is like another avenue for like studying like Hamiltonians, which is really interesting. Is like thinking about like the graph theoretic structure of like this. I mean, you can write like a 4 uniform hypergraph, or if you have like a degree 2 expression, like the bipartite case, where like you have like 2 batches of chi's and chi primes, and every term involves 1 chi and 1 chi prime. I think it's like both physically motivated and like a lot of the theory changes. Maybe you can get like better approximation algorithms in this case. So it's well worth studying. There are some results known actually, about, there might be, I don't know specific such results, but I think it's quite possible because like this bound, for example, is based on like the Lovász, understanding the Lovász theta function of a graph. So I think like if you get graph theoretic considerations of like your Hamiltonian into play, definitely things could change. I guess like maybe, okay, not in necessarily the fully anti-commuting setup, but like just in the general, I don't know, quantum CSP setup, I think the partite case is, I think, often or always, maybe for games, like considered more natural than the like unipartite case. So it's definitely a good area to study. And maybe you should check out So's paper. He might consider it. Okay, thanks for your attention.